I will talk about a European Defense Agency funded project that has been recently completed called Euroswarm, which entails the use of small UAVs, unmanned vehicles, and also ground vehicles. Thank you. Just a few words about where I work and where the university is. This is the Euroswarm logo and the project that I'll talk about. For those of you who don't know the University of Patras, and for the benefit of our overseas visitors and guests, Patras is at the top of the Peloponnese, and the University of Patras and the Aerospace Department is the only aerospace engineering school in Greece with a significant number of students, and we collaborate with the Air Force on multiple projects. The lab that I work for is the Applied Mechanics Lab as a research professor. The director is Professor Vasilios Kostopoulos, and the remit of the lab is working on composite multifunctional material structures for aircraft, satellites, vibrations, health monitoring, but also more recently, space technology and CubeSats or nanosatellites and autonomous systems. We have a very good track record with multiple European funded projects by the European Union, EDA, industry, the European Space Agency, and you can see a few pictures of some of the projects that we're working on. For example, high-resolution imaging through satellites that have a mass of 20 kilos, and high-altitude drones that we could fly for days, and power systems. This is a picture of a satellite that we flew last year, built by our students and other volunteers and members, entrepreneurs successfully, and this has led to the development of many advanced technologies, some which you will see that I will talk in the next 20 minutes. Euroswarm is a project which was funded by the European Union. It is a pilot project from the first round of defense R&D funding that the EU has initiated, managed by the European Defense Agency. We're very proud that we won this project amongst 27 other proposals, and it entails using unmanned heterogeneous swarms of sensor platforms. So ground vehicles, air vehicles, whether they're fixed wing, quad rotors, or different type of technologies. We've talked a lot about UAVs, drones, remotely piloted air systems. And I guess one of the benefits of being an afternoon speaker is that the morning speakers have done an excellent job to introduce a lot of these topics, and that would save me a lot of time. But it's without doubt that UAVs and drones are used very heavily now in defense and military applications. One of the older statistics that you can see here is that almost close to 10% of aerial attacks in Afghanistan in that particular year were done by unmanned aerial vehicles. However, most of them are still used as separate units, as monolithic sort of systems. And there's a number of reasons why that is happening. There is some research that is taking place, mostly in the United States. For example, working on swarms in very small scales or in larger ones like this one here, where DARPA and the Air Force funded an activity where F-18s dropped a very large number of small drones which flew around and tried to perform a surveillance and monitoring mission. However, it did have some limited autonomy capabilities, but it was one of the first demonstrations that have been published. So Euroswarm is an R&D activity which its goals are to develop novel techniques for adaptive, scalable, and robust operations of unmanned heterogeneous swarms. The goal is to integrate and validate existing technologies and to use it for a military scenario where you can protect a high-value asset, whether it could be an Air Force academy, a military base, or a nuclear installation. And we wanted to demonstrate that through practical demonstrations. We wanted to build some hardware and demonstrate the technical feasibility of this. Just to understand the context, this was a 15-month R&D project at around 434K euros and has been recently successfully completed. The principal investigator was Cranfield University, which I worked for at that time, Onera, the French Aerospace Lab, FOI, the Swedish Armaments Department Division, and Panepistimiou Patron, the University of Patras. So what is a swarm of heterogeneous systems? It is a group of static sensors and mobile sensing platforms. And in the acronym, and I appreciate we've seen a lot of acronyms today, the X stands for either air, ground, or even surface vehicles. And the goal is to obtain real-time, relevant situational awareness information that could help commanders and to help them optimize to make the right decisions at the right time. And a secondary benefit would be to reduce risk, human exposure, and contribute to military missions and operations. However, swarms come with their challenges. They are complex. They are, at the moment, limited in use because of the complexity and the levels of autonomy, limit levels in computational hardware, and this sort of has meant that perhaps we're using disproportionately assets for simpler or other tasks that could be done by unmanned vehicles. The mission scenario that we focused on working on is the protection of an asset, in this case, a base, and we use a group of air, fixed wing, quad rotor, and ground, but also static sensors in towers, which were able to get all the information together. The building blocks of our system are presented here, and you can see that these are technologies that are critical in order to formulate a swarm. And whether you're a pilot, a tank operator, or a helicopter user, these technologies are all very critical in order to operate any kind of vehicle in today's battlefield. You need tasking, you need failure detection, isolation, and recovery, you need situational awareness, guidance, and you also need to model and know your environments. And if you're working with a swarm, you need all of these to work together on each of these systems with the right level of computation. At the moment, what has been demonstrated is just connecting two of these two boxes depending on the testing and the platform that operators use. So our requirements, we wanted to use a fairly large number of drones. We used up to 10 drones, a combination of static, fixed wing, and UGV. So we actually ended up using something like 20 to 25, including the static ones. We wanted to integrate and make the operation autonomous. So we flew a mission in an airport for about 20 minutes, fully autonomously with using all of these systems and using sensor fusion, tasking, target tracking, and autonomy. And then our third requirement was to apply it to a realistic military scenario that was agreed by the EDA that was relevant, and to do this all through NATO architecture and NAF standards. The first technology that I will talk about is task allocation. And here you have a high number of tasks that you need to prioritize. You have a high number of agents, vehicles, and targets, and you need to decide with whom you will work with, how you're going to do this, find the optimal solution, and find the algorithm that can do this within the computational power and the availability of each of these drones have. Now, depending what drone you use, they might be very limited on their computational power. And again, remember that we're fusing sensors and data, big data, that is a very, very large amount of data. So the goal here was to develop an algorithm that could maximize the probability of target detection, and we were able to develop that. You see in this table some of the results. Just my laser pointer here is not working, but you can see that, for example, the reward function calculations, if you use an ideal solution, you get thousands of calculations that need to run on a simpler processor on a drone. However, there are algorithms that we've developed that you can reduce that by orders of magnitude. And this is some of the science and engineering that we were able to do, while at the same time maximizing and keeping the optimality to 100%. So we were able to do task allocation according to our scenario. Behavior monitoring is another key technology. You have some hostile targets. How do you really detect which one is hostile? With what metrics? So our objective was, again, to develop an algorithm that could help us detect these targets, hostile targets, and help us make the right decisions. Here you see a few plots. On your left-hand side, you see on the blue line is what a normal vehicle will do, a perimeter sort of trajectory that a normal vehicle starts from road 1 and passes a military base, which is in green in the middle. And then you have what we call an abnormal vehicle or a hostile target that loiters around this target. And our algorithm is very capable and is able to immediately detect with very few calculations a scenario like this. And obviously, we have run many, many more scenarios which are much more complex. But our algorithm enables us to save 50% in time to implement these algorithms on existing technologies. And that starts to build up a game-changing effect, which I hope you will see by the end of the talk. One of the other technologies that we worked on was how we can reconfigure a large number of swarms of drones that are able to monitor a target. On the left-hand side, you see 5 mobile vehicles starting from the 3 corners of that square. The blue circles are essentially static sensors and the range of these sensors. These could be radar, they could be pressure, they could be optical sensors. And then on the arrows, you see the swarm of 2 and 1 mobile vehicles going through and searching for what is a hostile target. Now, depending on when we have a failure, the whole swarm reconfigures itself in the most optimum manner in order to detect the hostile target. So on the top right-hand plot, you see 1 red circle on the top. That is a failed sensor. And the robot goes through it in order to detect it. It's using its mobile capabilities. On the bottom right-hand plot, you see 2 other circles where these sensors have either been destroyed or have failed, and our swarm is able to reconfigure immediately to cover for that loss of information. So, building up to integrate all of these, we used a number of commercial off-the-shelf drones that are available in the open market, which we slightly modified. And this included the Parrot Disco fixed-wing aircraft, Bebop 2 quadrotors, ground robots, hexacopters, and a whole number of assets that all of our partners were able to build together. We tested the algorithms from all these building blocks that I showed you before as a reminder. So our goal was to integrate all of this and see whether we can get a first principles approach and see whether the whole thing would work. One of the benefits of working at Cranfield is that Cranfield has an airport. So we were able to prototype a lot of these technologies at Patras, where we have a lot of open areas, but the official clearances and final testing happened at Cranfield Airport, which is a privately owned airport in Cranfield. And you can see the test area that we used to simulate this. There's a video here that I will show you one of the scenarios that we used for our final demonstration. There's a very large number of vehicles that we use. Here you see our fixed-wing UAV. This is a 1,000 euro fixed-wing UAV that we were able to modify with our software. So it does a very simple loitering operation, and it starts to detect all of the targets and the agents. We don't need the noise, the sound, if that's okay. But anyways, you can see that the guidance algorithm is able to move the UAV sequentially. You will see the fixed-wing agent at the top loitering. You see a lot of movement. At the top, you see our fixed-wing aircraft just doing a very simple trajectory, just like an AWACS would do on a large area. Then you have our agents taking off and landing as necessary, because our guidance algorithm is controlling it. And it's telling these drones, if we could kill the noise or the sound, that would be good. But anyways, the UGV collects the information, and you can see the ground vehicles are emulating hostile targets. And our swarm is trying to detect which ones are hostile, which ones are the most hostile, and which ones should be taken out. So you can see that there's a lot of reconfiguration, a lot of movement of these vehicles. There's the agents that are updating and taking still task allocation algorithms and following through the whole scenario that we have set up. So this is just a two-dimensional plot that shows you the targets and the agents. The T's are the targets and A are the agents that we were trying to command. And again, don't focus so much on the meters and the dimensions. This is a very scalable system. So if one was able to replace the small drones with bigger legacy drones, this system could potentially be implemented for other applications. So, of course, we learned a lot from this work. This was a pilot project. It was to learn, to do research, and to find what are the challenges. Setting up the architecture and the network was very challenging because we used drones from different companies, or even from the same company but bought at different times with different software versions. And it did take us a long time to get all of them to get integrated and to work together. Investment in sensor quality is incredibly important for the accuracy of your results. And again, a lot that has to do with the reliability that these companies claim that these vehicles have is very questionable, or at least is not always as they claim on their data sheets. So to summarize the achievements, we developed a test bed which enables demonstrating and verifying multi-agent swarm systems for asymmetrical warfare or for defense applications. It is a system that is fully autonomous, reconfigurable, and scalable, and to our knowledge, and as told by the EDA and the reviewers, this is one of the first implementations where successfully one has tested a fully autonomous swarm of unmanned vehicles at a small scale, of course. So to conclude, just a reminder that our project was funded by the EDA and the European Union. We were able to demonstrate some of the benefits that this could bring to the military in the following years if implemented. We performed a low-cost scale demonstration, and now we're beginning to prepare for phase 2. A lot of the partners that participate and member states at EDA have expressed, after our successful results, the backing of a follow-up, and they've proposed the University of Patras to do that. And we're working together with our MOD to see whether we could work jointly together on such a follow-up activity. I couldn't say too much about this other than the students and everyone who's worked in this project dedicate this work to the memory of Captain Baltadoros. And again, I would like to thank you for your attention.